So let's delve into chemical kinetics. Module 15a, we're going to talk about expressing the rate of a reaction in terms of the relative rates of disappearance of reactants or formation or production of products for a chemical reaction. Basically, how fast is the reaction going based on either how fast the reactants are being consumed or how fast the products are being formed. Before we get into kinetics, though, we really do need some base definition of what we're talking about here. So, chemical kinetics is defined as the study of the rates and speeds at which a chemical reaction occurs. Why should we care about this? Why should we care about chemical kinetics? Well, kinetics deals with how fast these changes happen, whether that be in minutes, seconds, our lifetime, well beyond our lifetime. How fast is it happening? Kinetics is the way that we study reactions to provide the best evidence to determine the reaction mechanism. So what do I mean by reaction mechanism? We're going to be able to define these a lot closer soon, but we're looking at a molecular level here. How is this reaction occurring at a molecular level? Sorry, I have the wrong setting on. There we go. So looking at the molecular level, how is this reaction occurring? In this chapter, we're concerned about two things. Calculations. I mean, it is chemistry gen chem class after all, right? But we're doing calculations involving reaction rates. We're going to talk about rate laws. You are specifically responsible for calculating zero order, first order, second order on integrated rate laws. But you will see rate laws that also go third order, fourth order, etc., depending on the reaction. The integrated rate laws looks at time. So rate laws themselves, again, can even go half order, so you can have fractions involved in these. We're going to show you how to determine the rate law of different reactions, but then when we get to the integrated rate laws, you're going to look at zero order, first order, and second order specifically. You're also going to talk about reaction mechanisms. A reaction mechanism is a step-by-step description of exactly how a reaction occurs. Remember, I said it at a molecular level. So at the molecular level, the reaction mechanism is telling us how this is actually occurring. What molecule is reacting with which molecule? What is happening? What's breaking apart? What's forming? We can't directly observe this because the particles are so small, right? Think about how small a particle is. It takes 6.022 times 10 to the 23rd atoms, particles, etc. to reach 1 mole. What if I'm talking about carbon? Carbon itself, this many atoms would weigh 12.01 grams. And I realize that you may or may not have a lot of lab experience, but 12 grams is not a lot. 12 grams contains all of those. Each atom is really, really small. We can't observe that, but we need to. We need to talk about how this is happening on a molecular level. That's where chemical kinetics comes in. The particles are so small, the individual steps occur so quickly that we can't do that without kinetics. We use chemical kinetics to get a window into this process. So again, as the reaction happens, the reactant molecules are colliding, bonds are being broken. Remember, bond breaking, endothermic, energy is required to break them apart, and new bonds are forming, exothermic, energy released. These are always. Bond breaking, always endothermic, requiring energy. Bond formation, always exothermic, releasing energy. So we have different terms we're going to use here. We're going to use rate, we're going to use rate laws, we're going to use mechanism, molecularity, all these different terms. And we need you to be clear with what is what. A rate itself is just the change in X over some unit of time. X being whatever we're monitoring, whether that be the consumption of a reactant, the production of a product, it doesn't matter. X is what are you examining at that moment. And it's the change in that. In this chapter, we're going to talk about the change in concentration over some unit of time. We can rewrite this as delta X over delta T. Again, delta means change in. So as the reaction occurs, the concentration of the reactants is decreasing and the concentration of the products is increasing because reactants are being consumed and products are being produced. The reaction rate, so rate is just change in X over change in time. The reaction rate, though, is the change in concentration of a reactant or product per unit time. Basically, it's taking stoichiometry into account. So the reaction rate actually considers your stoich. Reaction rate, change in concentration of reaction or product over change in time. We can represent this mathematically, and then of course we can write it with delta A, delta T. Why do I have a negative sign here? Reactants are being consumed. This is for, sorry, I used to have the reaction on here. This would be a reaction like A going to B. The change in A is being consumed. It is a reactant. The concentration is decreasing. So I put a negative sign in front to represent that it is decreasing over time. If I was doing this with respect to B, wrong button. With respect to B, the product, I would say rate is equal to the change in B over change in time, because B is a product and it's being produced. These brackets, by the way, I know that you may or may not have seen these brackets like this before. These brackets mean concentration, but specifically, they mean molarity. So when you see a chemical in brackets like that, not parentheses, actual brackets, the brackets mean that we're talking about the molarity of that substance. What are the typical units of rate? The units of rate are going to change depending on the reaction you're in, and we're going to show you how to determine, or I will show you how to determine the units on the reaction rate. But let me correct that, what I just said. Reaction rate units are always molar per second. I was thinking about your proportionality constant, which we haven't talked about yet. That one will change. But rate, always molar per second. And you can write it any of these ways. Remember, molar is molarity, so moles per liter, so that's where I get the moles per liter second. But rate is always molar per second, because I'm looking at concentration in molarity specifically over time, and most often seconds. Does every reaction have to be done in seconds? No. If a reaction is going to take 5,000 years, I'm not going to talk about seconds. Most of the reactions we're going to discuss will happen that fast. Until we get into half-life and stuff like that and radioactive decay, then we can see it take a little bit longer. But for the reactions you guys are doing, we're going to be talking about molarity per second. So how can I describe this reaction in relation to rate? Well, what if I've got A plus B going to C plus D? What are all these pieces? The lowercase a's here, A, B, C, and D, are the coefficients of the reaction. Right? That's your mole ratios. They're telling me A moles of A reacts with B moles of B to C moles of C and D moles of D. If I'm just talking about rate, I'm not talking about the rate law here, I'm just talking about rate, the reaction rate. I want to take stoichiometry into account. The way I would write it for this specific reaction would be rate equals, let's talk about A first. A is a reactant, so it's negative because its concentration is changing. And I've got a stoichiometric relationship here. I'm going to say 1 over A times the change in concentration of A over change in time. So you take that coefficient, that molar ratio, 1 divided by that to account for it in the whole reaction. It's negative because it's a reactant. This will equal negative 1 over B times the change in concentration of B over change in time. Note that the fraction I'm using is your molar ratios, so the lowercase letters, and the concentration is the reactant itself, so the capital letters. You could also say 1 over lowercase c times the change in concentration of C over change in time, but notice now this one is positive because I'm talking about a product. And you could say 1 over D, lowercase d because it's the mole ratio, times the change in concentration of D over change in time. Again, I'm using the fractions there for the mole ratio to bring this back down to a 1-to-1 level for them, because it's A moles of A reacting with B moles of B, producing C moles of C and D moles of D. The rate, negative 1 over A times change in concentration of A over change in time. With a reaction rate with respect to reactant B, negative 1 over B times the change in concentration of B over change in time. The reaction rate with respect to product C, 1 over C times the change in concentration of C over change in T, and the reaction rate with respect to product D, 1 over D, times the change in the concentration of product D over change in time. So let's apply what we've just talked about to an actual reaction. In this reaction, we have 2 moles of NO2 reacting to produce 2 moles of NO and 1 mole of O2. Everything's in the gas phase. We have 3 possible rate definitions for this reaction. We can say the rate is equal to negative 1/2 change in concentration of NO2 over change in time. The rate is equal to 1/2 change in concentration of NO over change in time, or the rate is equal to the change in concentration of O2 over change in time. Again, why do I have these the way they are? The negative sign here is because NO2 is a reactant. The 1/2 is because I need to account for the stoichiometry of the reaction. And then, of course, change in concentration. Here, the 1/2 to account for the stoichiometry of the reaction, and then the change in concentration of NO over time. And there's no fraction in front of O2 because I just have a mole of 1. 1 over 1, we just don't write it. But what if I was actually going to do this reaction in the lab? How could I measure this reaction? Well, we will do this in the lab as well, but the advantage to this is that NO2 itself is a reddish-brown color, whereas NO and O2 are clear. So we can actually monitor the disappearance of that color. So one thing we do in kinetics a lot is if a reactant or product are colored, we can monitor the color, either appearance or disappearance, of the reactant or product, whichever one it is. So we can use spectroscopy and monitor the disappearance of color to monitor how fast the NO2 is consumed in the reaction. Another idea would be we're producing O2. We could use an oxygen sensor and actually monitor the production of oxygen. So depending on what reactants and products you have, there's a number of different ways we can actually measure this in the lab, and that's how we can back up what we're predicting theoretically. So experiment always is the rule of the land kind of thing. So like experimentation is always the truth. We're just trying to predict what's happening based on what we're observing in experiment. What way can we do that though? We can do things like monitor the color, appearance, or disappearance of a product or reactant. We can monitor the production of O2. If O2 was a reactant, we can monitor the oxygen disappearance in the reaction, etc. So there's a number of ways we can do it. Sometimes you have to get a little creative and think outside of the box per se to see how can we actually monitor this. Kinetics is where we really start connecting that experimental world to our theoretical world. And we've been in the theoretical world a long time. So, what about comparative rates? What do I mean by comparative rates? I mean, if I'm comparing the rate of production of one product to the rate of production of another product, or the rate of production of a product to the rate of consumption of a reactant, the rate of consumption of a reactant to a product, etc. That is my comparative rate. I am comparing 2 different species, whether they be consumed or produced. So, if the rate of creation of O2 is 4 times 10 to the negative third moles per liter second, again, that's the same as saying molar seconds, then what is the rate of production of NO? Well, I know if I say that the rate of O2 creation is not the best of words because we can't create or destroy things. Law of conservation of mass tells us that. We can only change forms. But I see I've got 4 times 10 negative third moles per liter second, or molar seconds of O2. There's a 2-to-1 ratio here. I have 2 moles of NO being produced for every 1 mole of O2 being produced. So 2 moles of O2 to 1 mole of O2. That means that the rate of NO2 production would be 8 times 10 negative third molar per second NO. It's being produced at a rate twice as fast as O2 because I need to produce twice as much of it. So compared to O2, I have double the amount of NO. What about the rate of NO2 consumption? If I'm producing 4 times 10 negative third molar per second of O2, same thing, I use my balanced equation, my 2 moles of NO2 that are reacting to produce my 1 mole of O2, my 2-to-1 ratio here. But note, there's a negative sign in front here. Negative because it's being consumed. It is being consumed at a rate of 8.0 times 10 negative third molar per second NO2. So a rate of change of a specific species can be negative. This is not the overall rate of reaction. It's just telling me that the rate is negative because it's being consumed. It's not that it's really negative. It's a way for us to express mathematically that that reactant is being consumed in the reaction. So let's work some examples. How could you describe the rate of the following reaction? 2 moles of N2O5 gas producing 4 moles of NO2 and 1 mole of O2. Well, you could say negative 1/2 times the change in concentration of N2O5 over change in time. This specifically is looking at the rate of consumption of N2O5. You could also write negative 1/4 times the change in concentration of NO2 over change in time. This one is looking at the rate of formation of NO2. And we, of course, could talk about it by the rate of production of oxygen as well. We could say the change in concentration of O2 over change in time. And this, of course, as I just said, is looking at the rate of formation of O2. Are all of these equal? Are all of these, what I mean by these, are all of these equal? Are all of these expressions equal? No. No, they're not. The rate of formation of NO2 is the fastest. Why? Because I have to produce 4 moles of NO2. I've got 4 moles of NO2 being produced for every 1 mole of O2 being produced and 2 moles of N2O5 being consumed. So the rate of formation of NO2 is actually the fastest because I have to produce so much more of it compared to my other product and compared to the consumption of my reactant. So not all the expressions are equal, but the expressions, if I put the fractions in front and I consider their stoichiometry here, are comparative. It is a comparative rate. And I'm going to need space. So if you need to pause to write all that down. What is the relationship between the rate of formation of NO and the rate of formation of O2? If I look here, again, same reaction. I want to know for rate of formation of NO compared to the rate of formation of O2. The rate of formation of NO2 is 4 times faster than O2. Hence, that's why I write change in concentration of NO2 over change in time is equal to 4 times the change in concentration of O2 over change in time. Or I can write this as 1/4 change in concentration of NO2 over change in time is equal to the change in concentration of O2 over change in time. And again, when I wrote this, I don't remember if I wrote the negative sign in front for N2O5 or not, but it should have a negative sign here. Sorry, you guys. I'm so used to writing all this on a whiteboard. These slides are designed for a whiteboard, not a small screen. But there should have a negative sign in front of here because, again, negative for all reactants, because that delta symbol means product, or means final minus initial. So it's saying the final concentration of N2O5 minus the initial concentration of N2O5, that will be a negative value because the reactant has been consumed. What about this? Express the rate in terms of each reactant and product below. 4NH3 plus 5O2 give me 4NO plus 6H2O, everything in the gas phase. Rate is equal to negative 1/4 change in concentration of NH3 over change in time. This equals negative 1/5 change in concentration of O2 over change in time. which equals 1/4 change in concentration of NO over change in time, which equals 1/6 change in concentration of H2O over change in time. So again, always check yourself. Make sure that your reactants, make sure your reactants have a negative sign in front to account for the fact that they're being consumed. Products have a positive sign or no sign implying positive. Make sure that your coefficients become your fractions, because that accounts for the stoichiometry of the reaction. In the reaction, if nitrogen gas is being consumed at a rate of 2.7 molar per second, how fast is ammonia being formed? N2 gas plus 3 moles of H2 gas give me 2 moles of NH3 gas. Well, I know that I'm trying to find how fast is ammonia being formed. So I'm trying to find the change in ammonia over change in time. I know that hydrogen is being consumed at a rate of 2.7 molar per second, which is 2.7 moles of H2 per liter seconds. The balanced equation tells me I have 2 moles of NH3 being produced for every 3 moles of H2 being consumed. So the rate of production here is 1.8 moles per liter second, or you can say 1.8 molar per second. And some different things that can just affect the rate of reactions. We're going to talk a lot about these and talk about different reaction stuff, but I need you to have this kind of in the back of your mind. What are some of the things that influence the rate of reactions? Temperature. Generally speaking, the increasing of a temperature speeds up a reaction. Does that mean every reaction has to follow this? Of course not. Reactions can do whatever they want. We're trying to model them. We're trying to model nature. Nature's a complex system. But generally speaking, if I increase the temperature, the reaction will go faster. The general rule of thumb is that for every 10-degree increase in temperature, the reaction speed will double. The reactant concentration. If it's a homogeneous reaction, remember homogeneous means that it's all uniform composition, a higher concentration leads to more collisions. We're going to talk about the collision model in another module, but basically these molecules have to collide together with the right orientation in space and the right speed for a reaction to actually occur. If I have a higher concentration, it's more likely for more collisions to happen, and the more collisions that are happening, the more likely some of them will be successful. Not every collision is successful, but the more collisions I have, the more likelihood of collisions to be successful, the higher likelihood of the reaction to be successful. So concentrations of gases is dependent on the partial pressure of the gas. Don't forget we talked about partial pressures, Dalton's law of partial pressures and all of that. The higher pressure, higher concentration. So if I put pressure on gases, that means they're condensed down into a smaller volume. And if we have a smaller volume, more collisions, more successful reactions. Catalysts, we will talk about catalysts a little bit in another module as well, but a catalyst is a substance that affects the speed of a reaction without being consumed itself. It's actually used in a reaction, then regenerated, so it can keep being used in a reaction. It finds a different pathway for a reaction to occur. And the reason it does this is for the reaction to occur faster. The nature of the reactants. Generally speaking, gases react faster than liquids, liquids react faster than solids. Gases have more energy. They're bouncing around more. They're more likely to collide with each other. Liquids, they're still moving. Solids, generally speaking, will take a longer time to react because they're just sitting there. They're not going to have a lot of collisions happening. It's going to be a slower reaction. Aqueous reactions tend to be fast, very fast. Aqueous, remember, means you're dissolved in water. So if you're dissolved in water, those particles are moving around a lot faster, a lot easier, more likely for the reaction to occur. Larger molecules with stronger bonds will react slower. So covalently bonded will react slower. The compounds with strong covalent bonds will react more slowly than compounds with weak bonds. Larger molecules are going to react smaller than small molecules because they're just moving slower. Powdered solids are more reactive than blocks because of surface area. So if I take a solid and I actually make a powder of it, it's got a larger surface area, more likely to react, faster reactions. Certain reactions, certain types of chemicals are more reactive than others as well, so that can factor into the nature of reactants. Heterogeneous reactions, it's the state of subdivision of the condensed phase. Condensed means your solid or liquid phase in contrast to the liquid phase. The surface area makes a big effect on this. The reaction occurs at the surface of a phase transition. And I have electrochemistry with a smiley face here because this is my world. In electrochemistry, I have a piece of metal that I am electroplating onto. So I've got this piece of metal here, and so this is a metal electrode in solution. I've got particles coming up to the surface and leaving the surface. The entire reaction occurs at this surface. I can have a whole beaker here with all kinds of particles in it, but the reaction is occurring at this surface. It's completely dependent upon the surface area. So all of these things can influence the reaction rate, and many of them we will talk about more in depth in this chapter, but I need you to keep this in the back of your mind as we go through the chapter.